our airplane is solar powered. It has the same size as a normal piston propeller aircraft, and our maximum velocity is 120 knots, but the cruise speed is 110. Also, stalling will occur between 38 and 43 knots. Yes, maximum, our ceiling is about quite like just below 25,000 feet. So this is our flight envelope. And this is what we came up with first in the first weeks of design. And we ended up changing that with time, as Trendon will be able to explain now.
Well, I'll take over for the weight calculations. Can you put the dot in between the 1, 3, 1 and 2?
No. Yeah. One, three, one dots?
Yeah. Yeah, thanks. Alright, when designing an LSA, a light sports aircraft, there are very strict requirements in respect to weight. It has to be under 1320 for a regular land-based LSA or 1430 for a seacraft. But in our case, since we are designing a land craft, then we are limited to 1320. So initially, that's what we were going for. And when going through the weight estimations, in order to get as best weight as possible, we went through 3 different types of weight calculations. The first one was done using the aircraft performance textbook, using Anderson. We achieved a takeoff weight of 1307.3 pounds, fuel weight of 136, and empty weight of 810 pounds with a wing loading of 10.5598. This method was hugely based on using power loading. So we were trying to achieve a specific type of power loading. So after a couple of iterations, this is the one that best fit the calculation. Then we utilize the John Ruscombe calculations. Utilizing this guy is very famous when it comes to aircraft design.
Yeah. He
actually wrote about 7 books, dividing up the whole aircraft design process. We utilize book 1 in order to do the weight estimation for this plane. And with this method, using a non-linear method, we came up with a takeoff weight of 1316.7, a little bit closer to the 1320, because we wanted to maximize the amount of weight we could get from the aircraft. So we came up with 1316.7 for the takeoff weight, higher than the aircraft performance, but a lower fuel weight of 137.07 and 838.96. And then there were 2 different types of methods you could utilize in the Ruscombe method. The first one was, this particular one was based on just hand calculations, while the previous one utilized a nonlinear method in order to find the empty weight to takeoff weight fraction. With respect to the hand calculations, these are the values we were able to get. 13.16, 131 for fuel, and 840. But in the end, we decided to utilize the 1316.7 pounds, the 838.8 pounds for empty weight, and 131.0 pounds for fuel. Okay. So next we were the next part of the process was to figure out the best wing loading that we can have for our plane. So we utilize the method of we utilize carpet method in order to devise these figures. What's the carpet method? Usually on a graph you have two axes. You have the y-axis, which is your independent variable, along with your y-axis, which is your dependent variable. The carpet plot allows you to add several other independent variables, and depending on the figures you want, then you can utilize the sub variables inside of the graph to find the best value. So on this carpet plot, what we have the lift coefficients for 1.7 to 2.3. These are for your CL maximums, and the vertical lines here are your surface area, your reference surface area. So what we were trying to achieve was a cruise speed of 110 along with a stall speed of 38 knots. And by putting some lines on the graph and zeroing on a figure, we ended up with a CL maximum of about 21.1 something, 21.15 about for the CL maximum, and go back. Yeah, and 125 feet square for our reference surface area.
Where you learned this copy method?
Oh, inside side tree.
A new textbook?
The textbook that you saw with me the last time.
Okay. Anyway, we can continue on.
Okay. Yeah. All right. Well, as I said, we decided to go with these values. We ended up with a wing loading of 10.53.
Yep.
Okay, this part, I'm going to talk about the airfoil and wing platform. Our design aspect ratio is about 7.101, and the taper ratio is 1, and that, which means the wing tip, the length of wing tip over the length of wing root is all 1, and that means the shape of airfoil is rectangular, like picture down below is here, and no sweep and no dehedral. Wind reference area is about 125 feet square, and the wingspan is about 30 feet, and the mean geometry chord, root chord and tip chord is about 4.1956 feet. Okay, now, and we choose the NACA 2412.
You know what? When you say no sweeps, no dihedral, especially taper ratio is 1, actually you do not need to mention so many core lengths.
Oh.
I mean, it's a constant, right?
Yeah.
So, okay. Yeah.
Okay, we choose the NACA 24124 for our airfoil, and you can see the picture on
And it's 4.1956 feet.
yeah. Next page. Okay, this is data for NACA 2412. And this is our concept of our fuselage sizing and design. And you can see the bubble here. Okay, and we're going to take the solar panel on this wing surface. Okay, next page. Okay, this is a three-dimensional view of the aircraft.
This been done by CATIA or?
CATIA.
CATIA, okay. Have you considered to put solar cell on top of horizontal bed?
Yeah, we were considering that as well, but at the moment we have yet to actually install solar.
Not too much gain, right? Because how about elevator? No, you probably cannot just put elevator, put on the elevator part. Okay, please continue.
Yes, I wanted just to say that one of the advantages of having the taper ratio equaling 1 is having more area
Yeah,
for
that's what I thought.
yeah.
Yeah.
That's one of, we didn't want to have sweep angle or
Yeah.
any of that just because of the solar panels.
By the way, I just thought about one thing. Is how about make comparison with the other sports aircraft? How about a little dihedral angle? You know, you probably need to compare with the other similar aircraft.
Oh. Well, I think for most high wing aircraft, they normally have anhedral instead of the hedral.
Small angle.
Yeah, like a small, so like
Yeah.
about 3 degrees or so.
Okay. Yeah.
But I decided to go there.
And this is our fuselage link data. One pilot and one passenger, so total people is 2. And width of cockpit is about 3.667 feet, and length of nose, the nose end, is about 2 feet. The length of cockpit baggage is 7.5 feet, and fuselage diameter is 3.8442 feet. The wall thickness is about 0.0054 feet. Okay, next one. And there's 4 types of wing flaps, and we choose the flap type. So the lift coefficient improvement is about 0.9, and flap core is 0.8391 feet, and flap span is close to 80 feet, and 18 feet. Flap wing core ratio is 0.2, and span ratio is 0.6. Next page.
And I talk about the takeoff and landing. Analysis of takeoff fail length is 237.42 feet, and landing fail length is 242.857
So once again, this is a
feet.
calculated result,
Yeah,
right?
it's calculated
Too
result.
precise. Too good to be true. I mean, not wrong, but too precise, which is wrong. You can use, we talk about this.
Yeah,
We talk about this again and again, right?
Yeah.
Too precise is not good, it's a wrong thing, okay? 有效数值. But okay, please continue on.
Okay. And the landing gear we reference to Remus GX because we think it is low weight, and it is composite. And this landing gear is for pilot is easy to landing, and it less vulnerable to crosswind. Okay, and next one. And the horizontal and vertical tails are shown on there. Okay.
Okay.
And the next part.
So, I wanted to talk about what is it that inspired us. Okay, it's okay to dream about a world where you have a solar plane, but we cannot lie and say that, oh, we woke up in the morning and we decided let's do a solar plane. No, actually there is another plane very famous, the Solar Impulse, developed by Google, and that's where our inspiration came from. And the Solar Impulse is an amazing plane. Wait. The Solar Impulse is an amazing plane because First of all, look at the wingspan. The wingspan of a solar impulse is of about 63 meters, and it's the same as a Boeing 747. How can you have a Boeing 747, a jumbo jet, in your backyard? You cannot have. And that's why we couldn't actually be fully solar, because if you're designing a plane that is for normal people to have in their backyards, in their private airports, you need to rethink the concept of having a wingspan so long to accommodate all of the solar panels. And that's why we in the end decided to use an additional engine. Yes. So I just wanted to give you guys a glimpse of some of what we were dreaming of when we thought of our plane. And the solar impulse has,
for example, tail, they have
here.
solar sail.
Yeah, they have
Or even fuselage.
Yes.
Even fuselage.
The fuselage, all of it has solar panels. And the solar panel, they have a lot of solar panels. And the weight goes up to 633 kilograms, which makes the plane very heavy.
But all composite.
Yes, yes. The cockpit, okay. The ceiling is very high, and they go up to Mount Everest's height. Yes, the weight, despite its massive wingspan of 72 meters, okay, it's my mistake, 72 meters, the weight is actually pretty well, yeah. Okay, so back to our plane. Okay. So, even though we wanted to have a solar plane, a magic solar plane, we could not. And we thought of introducing a light engine to our aircraft to support the takeoff, and even when there is no sun, or because our solar performance is not so good, it's good to have this engine. At first, we wanted to go for another Rotax engine that would produce more power, but we figured that this one is okay because, well, we don't need that much power because the solar engine, the electrical engine, also produces thrust. It's a piston engine, and it's lightweight. It's a Rotax, the model 912 ULS.
Alright, this is our information for our aircraft performance with respect to the wing body calculations. This is our CD versus CL, and here we have our lift to drag ratios. And here the list of values. We went from a -10 angle of attack to 20. With the wing in particular, the wing by itself has a NACA 2412 has a maximum lift coefficient at angle of attack of about 15 degrees. So as you can see, oh no, this is CL. But yeah. And so these are values, and these will be listed inside of the inside of the report later. Oh, okay. Aircraft pricing and economic analysis. With respect to finding values for the pricing for our aircraft, we utilize a method called DAPCA. It was initially introduced for fighters, because before, fighters are highly advanced, and they use the latest materials, which can be very expensive. So you need to have like a ballpark idea of how much this would cost. And considering general aviation is an even bigger market, they try to initially adjust the DAP curve to general aviation, but it always was too excessive in price. So they found a new method, well, this DAP curve 4. And by using this method, we were able to test two different possibilities for our craft. We tested an all aluminum aircraft and 40% composite. The 40% composite which we intend to go with. And this idea takes into mind that in 5 years, we're gonna produce 1,000 aircraft. There are going to be every engineer is gonna work 8 days a week for a 48-week year. And we use the latest salaries with respect to different engineering positions. And what we came up at the end of it, the production cost, including $50,000 a plane for insurance, we came up with a production cost for all aluminum of $131,470 US. And for the 40% aluminum, we came up with $138,000 US.
Okay.
Oh, wait. And with respect to sales, and respect to sales,
so it's not totally ready yet?
me just first one more. Yeah, the cost for the craft.
Yes.
Yeah. So for the aluminum craft, at minimum selling price, inclusive of the $50,000 insurance, then we'll be selling it for $140,000. And for the 40% aluminum, for the 40% composite, it will be $149,000. Yeah.
This is affordable if you think about it.
You mean in US dollar?
Yeah.
150
Yeah, for the 40% composite.
million.
No.
No, 1,000.
1,000 dollars.
Yeah.
I have to calculate. How much is going to be Taiwanese dollar?
$10,000 multiplied by 3, 450, 4,500,000, give or take another 3, that's yes, by bath.
That's cheap.
Yes,
That's affordable.
yeah,
That's
4,800,000.
You mean only 4.5 million Taiwanese dollar? Wow, you can have 10. A lot of people will buy it. I mean, not in Taiwan. Go to Hong Kong. Okay, I think it's too cheap. It's for 2 persons, sit side by side, right? Okay. Not expensive at all. Not expensive. I think you underestimate. You underestimate.
No, that's not. I missed the
4000
zero.
万
I missed the
Yeah, doesn't sound right.
I missed the zero.
4000多万 ，400多万，不可能。400多万，400多万买2架放在
Yeah, I missed the zero.
顶上，4000多万 sounds right. Yeah. Okay. That's it. More?
Oh, yes.
Just one more thing.
Okay.
So in conclusion, no. Yeah.
So in conclusion, what we wanted to give you guys as a conclusion is that, I mean, clean energies can change the world. And if you imagine if everyone thought of having a plane that doesn't consume any fuel, which is not our case, but imagine that. Then people would feel that it's possible also to reduce energy consumption in their daily lives and maybe use more like electrical cars and stuff like that. I wanted to talk about the difference between what we had in mind in the beginning and what our final product is, and stress the process of aircraft designing, which is you cannot stay too fixed to an idea. If you have to change something because of constraints and because of trade-offs, then that's what engineers do. We need to adapt ourselves to what we find along the way. And one of the things we had to adapt to was if the payload and the range of our aircraft would be very, very reduced if we use solar panels. And the wingspan, of course, would be too large for a normal person to have. And these are the main differences, the main things that we had to have in mind during this whole process of
so
design.
It's not totally practical yet.
Yes.
Okay.
The idea we had in the beginning wasn't practical,
Okay.
but what we have,
total solar energy.
yes,
But right now you have
hybrid, yes,
Hybrid is making much more sense, right?
yes.
Okay.
And it also looks more like the first three aircrafts that we showed. So our plane is more like Cessna and the other ones than the Solar Impulse.
So during cruise is total solar energy, but takeoff, climb is hybrid. But have you mentioned the percentage of these two energy sources? 50-50 or 60-40? That's very important. That's very important.
With respect to the percentages, that there's as yet not a specific amount, because even for the hybrid part, the motor will just be assisting the internal combustion engine during takeoff. Because if you wanted to keep the same performance requirements that you had initially, particularly with respect to takeoff weight, then because the thing with hybrids, you need a battery. And batteries do not have the same energy capacity as hydrocarbons. So if you want to have like 50-50, for example, then you have to have a really large battery. And that will take away a lot from your takeoff weight, or you will have to sacrifice a lot. Because for our plane, in order to make the hybrid a possibility, we end up giving up 200 miles of range, 200 standard miles of range, in order to keep a reasonable payload. Initially started with 340, we dropped it to 320, so just 20 pounds, just because for payload had a very detrimental effect on the takeoff weight overall. So we, in order to keep the payload weight, we had to drop the range a lot. So in designing the hybrid plane, say 50% exact percentile is yet to be calculated. We have values that you will get in the report with respect to the changes in the weight ratios, but we do not have a percentile.
I forgot, but I haven't totally seen your weight calculation in this report. I mean, the solar cell weight, the battery's weight, and the engine's weight, and the fuel, and so forth. So the total calculation process is not showing here, but you did the calculation, right?
Oh yeah, we have the calculation.
Maybe you should show some of it
Yeah.
later on. But this is quite a professional product, right? You can make comparison of the three presentation. 你们看这三个报告，我觉得第一个看起来好像是